Okay, good afternoon to all of you. We will discuss today the rest of the questions and the theories of simple harmonic motion. I think we have to start from the equations. So first of all, we'll go along with the equations and the questions thereafter that arises with those equations, handling equations actually we have discussed today. So I have to now last day if I recap you what we did is we actually learned the definition of simple harmonic motion which says us that the force is directly proportional to the displacement from the equilibrium position and it is always acting towards the equilibrium position that we learned. Then that you must know because every year for 1 mark they ask this definition. Then we also need to know the special properties. We learned that also these things, so better keep it in mind. And I told you how to understand. I told that these are the three main equations that are governing displacement, velocity and acceleration, and these are the graphs related to these equations. But I told that these are not limited. For an example, they can give you a graph like this and tell that this is the displacement against time graph. You can tell like that. This is the displacement against time graph. And ask you what is the velocity against time graph. So last week we learned about that. Then they can tell you this is the displacement against time graph and ask you what is the velocity time graph. Then after learning that, we learned how to do this question. So today we will start from the waves, equations of the simple harmonic motion, some important facts, right? We know that the velocity equation is in simple harmonic motion, V equal A omega sin omega t. That is one thing. Then it tells us that if I want the maximum velocity, the maximum velocity would be actually A omega. When does it happen? There's a boundary condition for sin omega t. Sine functions, the maximum value that a sine function can have is +1. Then the minimum value that the sine function can have is -1. This negative sign indicates that the velocity and the uh, displace. This negative sign indicates that the velocity would be given by negative of these things. But when we are doing the calculations, we don't require the negative sign. So we just say when sin omega t, it's equal to 1. So when sin omega t is equal to 1, we maximum value, we are only bothered about the magnitude. So maximum value would be equal to what? A omega. Then if we know the maximum velocity, the next thing that we can approach is in simple harmonic motion, the objects that are oscillating. Now you know the maximum velocity and you know that the maximum velocity happens when the object passes the equilibrium position. Going down and going up furthermore, going down. So when it is oscillating like this, the maximum velocity happens when the object passes the central equilibrium. I think everybody can understand that. So when the object passes the central equilibrium, then this oscillating system would have the maximum kinetic energy. So we will find the maximum kinetic energy that is equal to half mv max square, which is found from A omega. So that is then half m a squared omega squared. This is not a standard equation, so don't use it directly. But you can write these two equations and obtain it and use it. There is a possibility like that. And then the next thing is, if this is the maximum kinetic energy. Now at the maximum displacements over here and here, at the maximum displacements, then the thing is, there the object starts to come to a momentarily stop. Why? Because the oscillating system needs to go down, it needs to stop and then move up. So here the velocity of the object would be 0. Now we know that energy cannot be destroyed or energy cannot be created. So it only transfers from one store to another store. So what would happen to all this kinetic energy at the maximum displacements? They all will transfer to potential. So if somebody asks then what is the maximum potential energy stored in an oscillating system, then this is the way to find it. Actually, we are finding the kinetic energy. That would be the maximum potential energy of the oscillating body. And I think that is fine. And by the definition, what is the definition? Force is directly proportional to displacement from the equilibrium position. And it is always acting towards the equilibrium position. Other thing, acceleration is directly proportional to displacement from the equilibrium position. And acceleration is always acting towards the equilibrium position. So, force and displacement, it would create an equation F is equal to minus k delta x. Acceleration equation, by the definition, the constant that we use to convert this direct proportionality into an equation is omega squared, angular velocity squared. Then if it is so, where would we get the maximum acceleration? It's actually not the position. What would be the maximum acceleration? The maximum acceleration would be at the place where the I mean, don't think that it's yeah, we can say maximum acceleration would happen if x becomes maximum, isn't it? What is the maximum displacement we can have? That is the amplitude. So this is, of course, you can use without proof. This one we can use without proof. This one we can use without proof. This one, better use it with the proof. Half mv squared, Vmax equal A omega. Therefore, Ek max equals half m A omega squared. Right. Then the next thing, now we have this idea. So we can calculate the maximum acceleration. Where the maximum acceleration would occur then? When the displacement, now here we know V is the maximum. Here V is the minimum. So in the maximum displacement of a simple harmonic motion, acceleration would be maximum. So where would acceleration be maximum then? At the maximum displacement. Right. Then definitions of simple harmonic motion. We need to know some basic definitions. What is called amplitude? Maximum displacement from the central equilibrium. What is called the time period? Time taken for one complete oscillation. When something is attached, it can go to a maximum displacement downward come up, and go down. This maximum displacement is what we call amplitude. Time period, if I start from here, the time taken for the object to go down, go up, go further up, and count down. One complete oscillation. Frequency, it's not like that. Frequency, I will keep a pin here. Then I will start the stopwatch. After 1 second, I will check how many oscillations have happened. Practically, that is not possible, so I'll tell you a method for that. So, number of complete oscillations, we have to add some more per 1 second. Number of complete oscillations per second. Then the next one, the wavelength. Wavelength is what? The distance between two adjacent points which are in phase. Is it valid to simple harmonic motion? Actually, simple harmonic motion would not cause any wavelength. But if we plot the graph of simple harmonic motion displacement, so it will lead us to a kind of an idea of a wavelength, but it's not that much 100% related. For the don't relate it to simple harmonic motion, but just remember that there is something like this. Then there are few facts that I need to highlight. Now, this is not there in the tute, but this is there for you to keep it in mind, because in the future we will write about them, right? What are the facts that we have to write? We have to know. When measuring the time period, this is very famous in Unit 6 papers. How do we correctly measure the time period? We'll first of all make a good setup. In what situations do we need to measure the time period? Simple pendulum. That is also under simple harmonic motion. First of all, we will say keep the timing marker at the center of oscillation. Keep the timing marker at the center of oscillation. Then next we will say start the stopwatch after few oscillations. Start the stopwatch after few oscillations. We let it to oscillate few times, and then only we start the oscillations. Then we will say when the stopwatch starts, start counting from 0, because when we start the stopwatch, it has not completed any kind of complete oscillations. So as soon as we start the stopwatch, we have to say what? 0. Then let's see like this. When an object is moving up and down, now I'm starting the stopwatch. So now I'm telling 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. As we complete 10 oscillations, we stop the stopwatch. Measure the time taken for 10 oscillations. Divide the time by 10 to calculate the time period. Divide the time by 10 to calculate the time period. Repeat and calculate the mean time period. So here it's not a repetition. Here 1 time 10p, and then we repeated and calculate the mean. Now tell me, Why do we need to measure the time for 10 oscillations? Because there is something called percentage uncertainty, which is uncertainty half the resolution of the stopwatch divided by time into 100%. You know this from Unit 3. When the time increases, what will happen to the uncertainty would remain the same because still we are using the stopwatch. Percentage uncertainty would reduce. So small percentage uncertainty means less random errors. It would reduce the random errors. Then repeating and calculating the mean also would further reduce the effects of random errors. Then the answer would be more closer, answers would be more closer to each other, right? So I told you some techniques to measure the time period of an oscillating body. That I think everybody is okay. Then the next one, the next thing, the next thing is how do we find the frequency? I told that it's not what I told, like, then I'll tell you something like this. Now, if you try to measure the number of oscillations per 1 second, there is an issue. What is the practical issue we have? Okay, now it moves. When it moves down, now I start the stop. It goes down, it goes up. Halfway mark, 1 second is over. So can you say that it's like half, three-quarter of a wave? Something like that? No, it's very hard. So we don't measure the number of oscillations for a unit time. Why? Because in a given time, if we try to measure the number of oscillations, the object may have not completed an oscillation. So there may be random errors occurring. So what we do is we measure how long will it take the time for few complete oscillations. So then what we do is we measure the time taken for 10 oscillations and then we calculate the time for one oscillation. And using frequency equal 1 over time period, we can calculate the frequency. That is right. Right. Now, I told you some additional knowledge because they are definite questions in Unit 6. Then we'll move on to 14.2. An object oscillates with simple harmonic motion. The period of oscillation is 0.55 seconds and the amplitude is 0.25 meters. Which of the following shows the correct calculation of the maximum velocity of the object? Now you can understand they're asking these questions, isn't it? So why do they give you the time period then? With time period, you will be able to find what? Omega. So what is the relationship between omega and time period? That we will come later, but for the moment I will give you the equation that is 2 by omega. Time period is equal to what then? 2 pi over omega. So omega is equal to what? 2 pi divided by time period. Now we know the omega value. Why do we need the omega value? Because they're asking the maximum velocity. Maximum velocity, we know that it happens at a omega. We learned that earlier. Then, do we know the amplitude? Yes. And the amplitude is 0.25. And omega value will be what? 2 pi divided by 0.55. So you have your answer. Is it there available? Zero point two five, 0.55. So answer is B. Then the next question. A mass oscillates with simple harmonic motion with a frequency 0.5 Hertz. Amplitude of the oscillation is 0.3 meters. Which of the following is an expression for the maximum velocity in meters per second of the mass? A mass oscillates with simple harmonic motion with a frequency of 0.5 Hertz. The amplitude of oscillation is 0.3 meters. Which of the oscillation is an expression for the maximum? Same idea, isn't it? But now they are giving us what? Frequency. So you can understand how questions change little by earlier time period. Now frequency. When they give you the frequency, then frequency is equal to 1 over time period. So that would be equal to 1 over 0. Sorry, then time period will be equal to 1 over frequency. That is 1 over 0.5. Then omega will be equal to 2 pi divided by 1 over 0.5. Then we can find Vmax, A omega. Then that would be what? A is equal to maximum displacement, which is for the amplitude 0.3, and omega will be 2 pi 0.5. By 0.5, 0.3. So the answer would be what? C. Then the next question, 14.4. Mass is hung from a spring and set into vertical oscillations. By displacing the mass 5 centimeters from its equilibrium position. Okay, we'll see how practically it happens. Center, it has displacement of 5 centimeters. So when the displacement is 5 centimeters, at that moment, the acceleration would be 8 centimeters per second. That should be squared. The graph shows how acceleration A of the mass depends upon the displacement x of the mass from its equilibrium position. When it is 5 centimeter, the acceleration would be what? 8 centimeters per second squared. When it is in the center, then little by little the displacement is reducing. That means it comes up. Then here the displacement would be 0. That means it would be what? 0 acceleration. It goes up. Sketch a graph on the axis below to show how x depends upon time. Sketch a graph on the axis below to show how x depends upon time. Okay. X stands for what? Our mass depends upon the displacement of mass from its equilibrium position. So initially then displacement, is it 0 or is it there? Yes, it's there. Why? Mass is hung from a spring and set into vertical oscillations by displacing the mass 5 centimeters from its extreme position. So when the time is 0, it has a displacement. You can either pick plus 5 or minus 5, doesn't matter. Pick plus 5. So downward then plus 5. Then what happened? The displacement graph goes down. Then we will have some grid lines when we are drawing oscillations. Always good for the health. No need to reduce our marks. Then in this question, according to one minute, they wanted actually one wave light, but in commonly in graphs actually they need at least 1.5 waves. So I'll try to go ahead with 1.5 waves. Always in the exam also, children, if you are drawing a graph, have some grid line. Now my grid lines are a bit ugly, so you keep the ruler and measure some lengths and draw, because even 1 mark matters. So 1 and 1.5 waves. Then do you think that they would give this actually 4 mark question? Do you think that they would give a 4 mark question just for drawing? No. Then there should be some markings, isn't it? One, I have marked the maximum displacement, but the time axis is empty. So time axis, you have to mark the time period. How do you mark the time period when they give you the maximum acceleration and the maximum displacement? You can find omega. How? A maximum acceleration is equal to A omega. So omega will be equal to what? Maximum acceleration divided by amplitude. Maximum acceleration is 8 centimeters per second squared. Amplitude would be 5 centimeters. So as they both have centimeters, I didn't bother about converting. Then this is 1.26 per second. Then from that I can find the time period of 2 pi over t, which is 2 pi divided by 1.26.
It's 1.6.
That's
1.6.
Oh, did I forget something? I forgot square. A omega squared. So omega would be the square root of this, isn't it? 1.26. Since Denita checked only, I remembered that. Then the next one. So 2 pi divided by 1.26. That would give us 4.97. So after finding that, please put the units. So here it would be what? 4.97 we will mark. Then that is done. So see, we did a 4 mark question that came from nowhere, no equations, nothing. They just gave us an acceleration against displacement graph where we had to understand, oh my god, what is this graph like? Now you know what is this graph. When the displacement is maximum, acceleration is also maximum. When the object is at the center, acceleration is 0, velocity is maximum. Then when the displacement in the other side maximum, acceleration also will be in the other direction maximum. Likewise, we can handle. Then These are the equations available for us in the formula sheet. Why I told like that is from there only I know that these equations are the main equations I can use in simple harmonic motion. All other equations, if there is any, we have to deal with proofs. That means not directly used. F equal k delta x, we learned. Force is directly proportional to displacement. A equal minus omega squared, we learned. Acceleration is directly proportional to displacement. Displacement, velocity, acceleration definitions, we learned. Time period, we know. Omega value, we know. This one, still we know this one. M over K, where M is the mass hanging, K will be the spring constant. This one on the way, there is for a simple pendulum. If a simple pendulum is making simple harmonic motion, going this way and this way, then this would be the length of the simple pendulum. This is the gravitational field strength, and this would be the time period. The other importance is actually this equation is helping us to find the gravitational acceleration. Right. So in the future, we will meet it. Now we will move on to this question. State 14.5. Now, when you are stating the conditions necessary, be always very careful and vigilant on how the question is being asked. So in here, it's just a matter of they are just state the conditions for the mass to undergo simple harmonic motion. So that is a direct open question. So we simply say what the acceleration is directly proportional to a displacement from the equilibrium position. And this acceleration is acting towards the always acting towards the equilibrium position. Or else there's another method, that is what force is directly proportional to displacement from the equilibrium position. And this force is always acting towards the equilibrium position, that we can say. Now there is a full question on our way. What is the full question? They are asking calculate the maximum kinetic energy. So as I told you, you can't use that direct equation. Hence, what can you use? What did they give us? Mass. 0.2 kilograms. Spring extends by 16.5 centimeter when the mass is added to the spring. So, then this is not maximum amplitude, okay? When we add the mass of 0.25 kilograms compared to its initial position, the spring got extended by 0.165 meters. Why do they give that? You can find K. The mass is then displaced further 3.5 centimeters. From the resting, the mass is further displaced. 3.5 centimeters. Vertically down. That is what the amplitude and released. The mass oscillates with simple harmonic motion. Calculate the maximum kinetic energy. Okay, we'll start with what we need to find first then. If we need the maximum kinetic energy, we need what? Half m v max square. If we need that one, we need what is v max square. V max will be equal to what? Minus a omega. If we need that A is known 3.5 in 10 to the power minus 2, omega we need to find. Omega is equal to what? 2 pi over, did they give us anything? No. Omega is equal to 2 pi over capital T. Then if we need to find omega, we need to know what? T, which is equal to 2 pi square root m over k. So now I gave you a full plan. What I need at the end. To find that one, what I need is Vmax. To find Vmax, I need omega. To find omega, I need T. That's how examiners make questions. They start from here and make the question without giving one information. Examiner know, okay, if I ask the student to find the maximum kinetic energy, I should not give Vmax. If I don't give the student Vmax value, then I have to the student have to use Vmax equal A omega. Then examiner will decide, alright, okay, out of that I will give A, but I will not give omega. Then examiner will be thinking, okay, if the student want to use omega, omega is equal to 2 pi over T. So then I will not give T. Then instead I will give M and K so the student can find T. Now examiner prepared the question reverse way. Then the student have to go in what? The opposite direction. So if you start the question, the analysis from the place where what you need, you will realize where you should start. The thing behind this lesson is actually that. What? There are so many equations. That's why I spent a little space in my tube giving you the equations that are already there in the formula sheet. Why? Because they are available for you. It's a matter of utilizing them. Pay and utilize. Now, we'll find. So, you know the K value. Do you know the K value? Oh my god, K is also unknown. Then what do you have to find? K. How do you find K? F equals K delta X. Then, do you know delta X? 3.5 into 10 to the power minus 2. Do you know force? No. You know the mass. So the force not 3.5, sorry. The mass of 0.25 would make a displacement of 0.165. So the force will be equal to 0.25 into 9.81. Okay. Delta X would be equal to when we hang a mass of 0.25 kilogram, the spring extends by 0.165 meters. From there, I will get the K value. When I substitute that K value here, mass of the spring mass system is 0.25. K value we found. From that, we will get the T value. I hope someone would help me to find the T value. Mass is 0.25. K is obtained from here. Then use that T value here. I hope someone would help me to use that T value and find omega. Use that omega. I hope someone would use that omega and help me with A to find Vmax and finally the kinetic energy. Can somebody tell me the values after calculating?
So K value is 14.8.
14.8 Hamson.
14.86 K value.
K value. Okay. K value is 14.86. 14.86 units would be newtons per meter.
T is 0.815.
814 seconds. 0.814 seconds time period.
Omega is 7.709.
7.709 per second.
So here the amplitude is 3.5 centimeters.
Amplitude is 3.5 centimeters. We will use converting it into meters because from the resting position, maximum displacement.
Okay, 0.269.
Meters per second.
9.045 into 10 to the power minus
9.045
45.
into 10 to the power minus
3.
3 joules. So I made sure that units are placed everywhere just for your practice. It's always a good practice to use the units. 1, 2, 3, 4, 5. Then we will move on to this one. The graph shows how displacement of oscillating mass varies over 2 cycles. Add to the graph to show how kinetic energy of the mass varies over the same time. What you need to know is kinetic energy is actually what? The velocity is the speed squared. Kinetic energy is a scalar quantity, so kinetic energy would never become negative. Kinetic energy would never become negative. So we can say that better we will have a rough sketch of how the velocity graph would look like. Can you remember how to draw the velocity graph when the displacement graph is given? How? If the displacement graph looks like this, go quarter ahead. This would be the shape of the velocity graph. But I have to draw it from the beginning. So now I understood the shape. Now I will draw. So I will have to have some good grid lines. No need to be the same shape because now we are using the same y-axis for another quantity. So you can draw it either bigger or smaller, doesn't matter. But of course must be matching with the time period of the displacement or velocity or acceleration. All the three graphs should maintain the same time because the time taken to make one complete oscillation doesn't change. So these are good practices, children. Otherwise, I would have also not drawn these things. I would have just told you, oh, okay, we'll draw like this. No. Then this is done. Then what do you have to do? How do we draw the velocity time graph? Part ahead, then we recognize the shape. This is the shape of the graph that you need to have. So we will draw it now. I will draw it a bit bigger for our better understanding. Every quarter, I have to complete part of a wave. Then the next thing, now you've got what? The velocity graph. Then I'm now this line is what? Velocity, okay? Now I'm going to, now in the exam, you draw it and get the idea, or draw it separately and get the idea only. Now I'm going to draw the kinetic energy graph. You know, when the velocity is maximum, kinetic energy is maximum. When the velocity is zero, kinetic energy is zero. When the velocity is negatively maximum, also kinetic energy would be positively maximum in the same value. Because even though positive or negative, let's say the velocity is plus 5 meters per second, then the maximum negative velocity would be minus 5 meters per second. So it won't vary when we put it to v square. Then again, when the velocity is zero, kinetic energy is zero. When the velocity is maximum, kinetic energy is maximum. When the velocity is zero, kinetic energy is zero. When the velocity is minimum, that means negative and maximum, kinetic energy is also positive and maximum. 0, positive and maximum. That's how it is. Now we are ready to draw the kinetic energy, same shape. We have a bit space to turn. I hope all of you understood, as the kinetic energy cannot become negative. Then that's how it is. So now I'm going to remove my velocity graph. So I got my kinetic energy graph. I think everybody understood that. If any issues are there, tell me. So we got 2 marks. But 2 marks would they give for the shape? Is there any possibility we can? There is a possibility. So better mark. 9.0 or 9.0, 10 to the power minus 3. And this is 0. Done. Then we'll move on to this one. This question is different. All the other questions, they stated state. This question, they are telling explain. Why not the definition? Why the mass moves? Why the mass moves with simple harmonic motion? It's not because of acceleration. Mass will start to move because of what? The force. So this simple harmonic motion origination happens from the force. Force causes acceleration. Acceleration causes motion, isn't it? That's how it is. So the story starts from where? Force. Why the mass moves? Because of the force then. So here, if a student write acceleration, there will be an issue. So here you are going to write what? There is a force acting on the mass that is directly proportional to the displacement from its equilibrium position. There is a force acting on the mass that is directly proportional to the displacement from its equilibrium position. And this force is always acting towards the equilibrium position. Definition, but in the force side. When the mass on the end of the spring was 0.2 kilogram, extension is this. So similar question is it. They have given the mass and they have given the extension. This is not actually the amplitude then. This is what then when we hang a mass, this much of extension is shown. When the mass was in equilibrium, show that the stiffness of the spring is about this. So earlier it was a part of that 5-mark question, isn't it? Then F equals K delta X, K is equal to F divided by delta X. Force 0.2 into 9.81 divided by delta X value would be 7.5 into 10 to the power minus 2. The student used a stopwatch to determine the frequency of oscillation F of the mass M. She repeated this procedure for 4 more values of M and obtained the following graph. The student used the graph to determine the value for K. Deduce whether the graph gives the value for K consistent with the value in 1. 6 marks. So here what do they expect? They expect you to find the spring constant using the graph. When they give you a graph, there will be some kind of relationship between frequency squared and per mass, isn't it? So if I just see the gradient would be f squared divided by m to the power minus 1. That is f squared m. F squared m. Is it having any kind of relationship? F squared. F squared is 1 over t squared. M over t squared. Yes. I'll start with the equation. T equal 2 pi square root m over k. Without this start, we will never be able to go for a particular idea. Unless you can remember that f squared against per mass is a graph that is possible in these simple harmonic oscillations. 1 over f is equal to 2 pi square root m over k. 1 over f squared is equal to 4 pi squared m over k. I'll take the reciprocal of everything. F squared is equal to 1 over 4 pi squared. This m goes down, k goes up. K I will write here, m I will write here. It's done. Now it looks like what? Y equals m x. Good to know, isn't it? Then the gradient will give us, we calculate the gradient. We can calculate the gradient by taking 2 good points. This is 3 and 4.6. is also better. That would be 0.4 and 0.8. Y difference 3 minus 0.4, X difference 4.6 minus 0.8. And the gradient will be equal to what? K over 4 pi square. Three minus 0.4 divided by 4.6 minus 0.8. Which is 0.6.
I'm getting 27.
And Sandhu?
So I took the furthest 2 points. Then I got 27.02.
For the K value.
Yes.
Ah, 0.684. So from here we get K equal 0.684 multiplied by 4 into pi squared. 27.
27.0.
27.0. So F over delta X, that means newtons per meter. Furthest point, are they good points? This one is in the center, like that.
Yes, I took. Then it's 3.15.
3.15, okay. Good. But it's always better, less random errors when we use a point on a cross, isn't it?
Okay.
Yes, then that we will get a value. Then we found the K value. Now we found the K value. So then we have to comment. Then how do they allocate the marks? For this and identifying that it's in the form of y equal mx. Before that, for this, 1 mark was allocated. Then comparing this one, so you would say this is, this is in the form of, don't just write this, y equal mx. Then finding the gradient. Then identifying the gradient, that is also under the part of mark 2. Then large triangle used to find the gradient. That's why we took further away points. Then finding K value. Then lastly, the comment. The comment is whether it is consistent or whether it is not consistent. What was the previous K value that we found?
26.16.
Newtons per meter, yes. So then we can say what? All right. No way. So we can say what? Therefore, 27 newtons per meter is not equal to 26.16 newtons per meter. Therefore, they are not the same. So always go for a conclusion from what you're finding. Unit 4, Unit 5, Unit 6, always go for a conclusion. Right. Then 14.7 homework. Simple harmonic motion. Before going to simple harmonic motion, actually I should have placed this 14.8 on top of this question. So I will finish this question. Then after that I will move on to the simple harmonic motion of simple pendulum. A student hangs a mass from the end of a spring and sets motion into vertical oscillation. So because this is a spring mass system. The period of oscillation of the mass is t. The student then hangs the same mass from the second spring with a spring constant 4 times that of the first spring. What is the period of oscillation of the mass of the second spring? So it always goes with then what the equation. Do they ask about the frequency and spring constant or time period? What is the period of oscillation? So time period. And they are talking about the spring constant. So we will start with the equation. What time period is equal to 2 pi square root m over k. Now I'm going to find the new one. So we see about the new one, then time period. New time period would be equal to 2 pi new mass, new swing constant. I kept some space so that if I have to include a number, I will have to include that number also. Now they are telling the student then has the same mass, So this would be constant from a second spring with spring constant 4 times. So the new spring constant is 4 times. So I had to include in the denominator 4 inside the square root. Mathematically, can I do like that? No. So if I want to introduce in the right hand side 4 in the denominator, in the left hand side also, I have to introduce a 4 in the denominator. So it leads to what? T over 2. So the answer becomes what? T over 2.
So is it 2T or T1?
T over 2. Why? Because this side, the K value, now tension and the spring constants are, tension is inversely proportional to root of spring constant. So whatever the thing happens to the spring constant, opposite should happen to the tension. Time period. Not tension, time period. So if the spring constant becomes 4 times, time period should become 1 over square root 4 times. That is 1 over 2.
Yeah.
So then done. Now I'll move on to simple harmonic motion, actually oscillation. So this is simple pendulum. Simple pendulum, as I told you earlier, in simple pendulums, what we can do is in simple pendulum, what we can do is the equation that governs simple pendulum is this. That is the equation that is given in the formula sheet. So if you ever want to go for a graph or comparison like what we did earlier, so better know how the equation is handled. So the equation can be handled in this way. What is that? T is y and square root L is x. And L. So if a student goes for a graph of T in y-axis and square root L in the x-axis, the gradient will be equal to 2 pi over square root g. Then g would be equal to 4 pi squared over gradient square. If a student goes, now we can square everything in this one. So if a student goes for t square against L, then the gradient would be equal to 4 pi squared over g. So g will be equal to 4 pi squared over gradient. This is what y equal mx. T square against L, this one. T against root L. So, right. SI system units was established in 1960. There are 7 base units in SI system, including the meter, which is a base unit of length. Give the SI base units of energy. What is the SI base unit of energy? It's not SI unit, it's SI base unit. What is the SI base unit of energy?
Kilogram meter square second to the power minus 3.
Kilograms meters per second to the minus. We see how the energy comes from. We'll forget everything. We'll go for a better equation for the energy. Energy is actually it's actually the work done. Work done is equal to force multiplied by distance. Force is mass, acceleration, and displacement. Then mass kilogram, acceleration meters per second squared, distance meters. So kilograms meter square per second square. Isn't it right? Kilograms meter square per second square. Yes. In 17th century, hygiene suggested that unit of length should be defined by the length of a second's pendulum. This is a simple pendulum that takes exactly 1 second to swing from one extreme position to the other. So it's not one complete time period, then half a complete time period. So it took 1 second. The second's pendulum took 1 second to go from one extreme end to the other. A simple pendulum that takes exactly 1 second to swing from one extreme position to the other. Calculate the length of a simple pendulum that swings from one extreme position to the other in 1 second. So, what is the equation we have? T equal 2 pi square root L over G. Earlier M over K, now L over G. T1. Oh, that's wrong, isn't it? Calculate the length of the simple pendulum that swings from one extreme position to the other in 1. So if it takes 1 second to travel from one extreme point to the other, then it has to come back again for one complete time period. So time period should be 2 then. How deceiving, isn't it? 2 pi square root L over 9.8. And we get what?
So 0.994.
0.994.
4.
0.994 meters. So it's not actually 1 meter, right? Then your length should be defined by the length of a second's pendulum. Right, anyway. Suggests a disadvantage of basing the meter on the length of a second's pendulum. So then if anybody wants to say, okay, I have 1 meter, then we have actually base units in the world. So there are proper definitions for them. So if somebody says I have 1 meter because my pendulum took 1 second to travel from one extreme to the other, so the length of my pendulum is exactly 1 meter, would it be correct or would it be affecting some external factors? Otherwise, there should be no. Then when basing something, there shouldn't be any control variable actually. Of course, there can be, but there should be conditions there. Then what will happen if we do this experiment in on top of a mountain? Gravitational field strength, would it be 9.81? No. Isn't it? Then so what would be the answer? L varies with G, but G varies with the location. And in different locations, 1 meter would be different, but 1 meter can't be different like that. Right. Then the graph shows how the velocity of the bob varied with time. Add a line to the graph to show how the displacement of the bob varied with time during the same time interval. Add a line to the graph to show the displacement. This is what velocity. You know how to travel from velocity. Now, velocity shape that they have given is what I will refrain from drawing this vertical axis. They have given the velocity shape like this. If you want to go to the displacement, add quarterback. If you want to go to the acceleration, delete quarter forward. Then this is the acceleration shape. Right. So now you know what is the shape that you have to draw. The shape that you have to draw is what? This is the shape that you have to draw. So we'll draw that. I will, for my easiness, I will reduce that value. But can I change the time? No. Time period would be the same. Starting from here, part of a wave, part of a wave, part of a wave, water, water. So I draw the displacement. Then determine the length of the simple pendulum. Length of the simple pendulum T is equal to 2 pi square root L over G. So L will be equal to T square 4 pi squared G. T. Two. Time taken for one complete oscillation. G 9.81. 4 pi squared. You will get the answer. Answer
0.497.
Oh, I did a small mistake. It should be 2 squares on it. So Hemsandu's answer should be doubled.
0.994.
In some experiments, it is an advantage to use data logger rather than other measuring instruments. Describe when the use of a data logger is an advantage. Now, data loggers are always used with sensors. There are several ways that data loggers, when connected with sensors, can be advantageous for us. Number one, they can measure data without human reaction time. What data? Simultaneous data. So one advantage is what? Simultaneous data. That means two data at one instant. Humans can't do that, isn't it? Let's say stopwatch and temperature. When you look at the stopwatch, it's 10 seconds. As soon as it is 10 seconds, you look at the thermometer and get the reading. But when you finish getting the reading, it's not 10 seconds, it's like 12, 13 seconds. So reaction time of 3 seconds, like it's there. We are not that fast. But if it is a thermal sensor connected to a data logger, it exactly measures the temperature at 10 seconds. Then there is, so how are we going to tell that to get marks then? Data loggers connected to sensors can take simultaneous readings without human reaction time. Now, I'm not telling the answer to this one, I'm telling some advantages commonly. The second one is the data loggers can take, connected to sensors, can take many readings in a small time interval. In a short time interval, many readings can be taken. That means high sampling rate. So how are we going? What are the things that we are going to write then? Number one, not for this one, common things. Simultaneous readings can be taken or synchronous readings can be taken without human reaction time. Number two, can take many readings in a short time interval. Number three, data can be taken over a long period of time. Data can be collected over a long period of time. Then generally those are the things. So here, it's in some experiments it is an advantage to use a data logger rather than measuring instruments. Describe when the use of data logger is an this is actually open question. So we can write any two from what I told. Then one is what? Many readings can be taken for short time interval. Number two, multiple data sets have to be collected simultaneously, can be taken without human reaction time. Multiple data, when they need to be taken simultaneously, they can be obtained without human reaction time. Or you can even say, when the data needs to be collected over a long time interval, data logger can be used. Right. So the first part of oscillations is done. Now we are moving on to the second part, forced oscillations and resonance. Forced oscillations and resonance. In forced oscillations and resonance, first of all, we have to understand that there are two things in this lesson, driver and the driven. For an example, one example, when you're playing a guitar, the guitar string vibrates. When the guitar string vibrates, the air particles near the guitar string also will start to vibrate. In that case, the driver will be the guitar string, the driven will be the air particles. So a vibrating body which is used to transfer energy to another object and to cause that to vibrate is what we call the driver. Then an object that gets vibrated due to the energy given by the driver is called driven. So in this example, string is a driver, air particles will be the driven. That is number one. So now you know the first idea about the driver and the driven. Then number 2. What is meant by forced oscillation? What you saw is actually forced oscillation. When a driver vibrates, now I'll relate it with this one. When the string vibrates, energy transfers from the string to the air particles. Hence, air particles are forced to vibrate with a frequency equal to the frequency of the string. I'll tell it again now. This is how commonly I can say. Now I'm converting it into a situation. When the string vibrates, energy transfers from the string to the air particles. Hence, the air particles are forced to vibrate with a frequency equal to the frequency of the string. This third point sometimes is not valid. An example like this. So we have to cut one word here. When pendulum X vibrates, this is a simple pendulum system. One pendulum is hanging, the other one is a shorter pendulum that is also hanging. When pendulum X vibrates, energy transfers from pendulum X to pendulum A. Hence, pendulum A is forced to vibrate. That's all. This is due to forces because in this case we can't say with a frequency equal to frequency of X because A has its own natural frequency. So A will vibrate on its frequency. A will vibrate on its maybe This is actually another situation under forced oscillations. In this one also you can see when we are explaining, I can't now okay at this instant when we make this one to move, so this is actually forcing the spring to oscillate. So in here this is under forced oscillation, but in here we can't say that frequency of this one's oscillation is equal to frequency of this one's oscillation, but still it becomes a forced oscillation, right? So we will keep it in mind that forced oscillation, that frequency thing is not always common, right? So this last one, handle with care. There are situations where you have to use, there are situations where you can't use it. But then this one, resonance. When a driver vibrates, now resonance is a different idea. The resonance is also a part of forced oscillation, but it has a special condition. That is, I would be talking about a pendulum that has the same length as the pendulum that is already oscillating. Why? Because this is also t equal 2 pi square root L over G, then same L, here also same L. So they both have the same time period and they both have the same frequency of oscillations. So this usual oscillation that a oscillating body have, that we can calculate it using the standard equations, that frequency is actually what we call the natural frequency of an object. Natural frequency of an object. Right? That's how it is. Then when we talk about this one, then what is the natural frequency of this one? You can calculate. But if I use the other one also with the same length, that one's natural frequency and the driver's natural frequency are the same. It doesn't happen here. Why? The length is different. So if two bodies are there with the same natural frequency, a special event is occurring, that is, here to here the energy is transferring. So the pendulum A will be forced to vibrate due to forced oscillation. But pendulum X to pendulum, let's say B, the energy is transferring, but it would transfer at a greater rate. So if this one vibrates with an amplitude of 1 centimeter, this one would vibrate with the maximum possible amplitude. That is under resonance. So the basic condition is their natural frequencies are being the same. So when a driver vibrates with a frequency equal to the natural frequency of the driven is forced to vibrate at its natural frequency. So maximum energy, the driven is forced to vibrate how? At its natural frequency. In that case, what will happen? The maximum energy would transfer from the driver to the driven at its greatest rate. Then the driven will be forced to vibrate with greatest energy and maximum amplitude. Now, how do we say so? A is not under natural frequency, which is equal to natural frequency of X. B is also not, because their lengths are different, their frequencies are different. C and X have the same length, so same natural frequency. Pendulum X vibrates with the frequency equal to natural frequency of pendulum C, because X and C have what? The same length, both have same natural frequency. So pendulum C would be forced to vibrate at its natural frequency. Hence, maximum energy transfers from X to C at its greatest rate. And C is forced to vibrate, that's true, but maximum energy transfer, therefore, it's a special condition we say, but that is due to resonance. So Then finally, we'll add one that is also a mark point. This is due to resonance. Okay, now we'll see 14.11. And says what? Forcing a system into oscillations may result in resonance. For resonance to occur, the oscillating system must be driven at its natural frequency. When a train travels across railway bridge, the bridge may be forced into resonant oscillations. Which of the following happens only when resonance occurs? When a train travels across a railway bridge, the bridge may be forced into resonant oscillations. Which of the following happens only when the resonance occurs? Damping still we didn't learn. Damping reduces the amplitude of oscillation. Energy is transferred from the train to the bridge. It is always happening. Even under forced oscillation, also it is happening. Resistive forces dissipate energy from the train, that is under damping. We will learn it in the future. Amplitude of oscillation is unusually large. Resonance. Maximum energy and amplitude. Photograph shows a nodding tiger toy. The tiger toy is placed on car's dashboard and the head nods up and down as the car is driven along a rough road surface. It is noticed that at a particular speed, the tiger's head vibrates with maximum amplitude. What is the name of this phenomenon? Maximum amplitude word is seen, isn't it? When we read maximum amplitude, what comes to your mind? Resonance. Describe the conditions necessary for this phenomenon to occur. Right. The vibrating frequency of engine, vibrating frequency of engine will equal to what? Natural frequency of tiger. So in that case, it's not now. We said under resonance in the definition I told, when a driver vibrates with a frequency equal to the natural frequency of the driver. That is the condition, isn't it? When the engine vibrates with a frequency equal to natural frequency of the tiger's head. The tiger's head is forced to vibrate at its natural frequency. Maximum energy transfer from the engine to the tiger's head at its greatest rate. So the tiger's head is forced to vibrate with greatest energy and maximum amplitude. This happens due to resonance. So these just describe. We only need to write this. Then the graph shows how the variation of acceleration time is happening. Using values from the graph, calculate the amplitude of oscillation of the tiger's head. It comes with maximum acceleration. With time period, Time taken for one complete oscillation, 0.8 seconds. We can find omega. Then we can substitute that omega here with the maximum acceleration of 1.2. Then you can calculate the answer. Someone can help me?
Zero point zero one nine five.
0.0195 meters. Sketch the graph of the head's displacement against time over the same time. Displacement, acceleration, quarterback velocity, quarterback displacement. So it should start like this then. We'll have the horizontal grid lines. Done, but we have the possibility of finding the maximum displacement because 2 marks are there. We found actually 0.0195, which is plus 0.0195. Done. Then the last part of simple harmonic motion, that is the damping situation. In damping questions, there is a graph that I need to teach that is not there in this note. So I will teach you about that one before I go to this situation. Now, damping, you all need to know what is meant by damping. If we keep this spring mass system in a water, you will see that it's actually not vibrating with the amplitude that it is usually supposed to vibrate because it is inside water. Because there are some drag forces that the water is exerting on the oscillating body. When we take it out, then we see that it's vibrating with much greater amplitudes than possible, isn't it? That we saw inside the water. Reason is actually damping. So if I try to draw the displacement against time, for a usual situation, that means undamped situation. That would look like this. Now, if I draw displacement time graph for a damped situation, it would be something like this. initially, as it is starting with the same displacement, there wouldn't be any changes. But little by little, what will happen is now it goes down. But now energy is dissipated to the surrounding. So it won't give the same amplitude as earlier. We'll have a reduced amplitude. I just drew some guidelines to reduce, but I'll erase it. However, it should be foreverly reducing. Okay. Then compared to this one is smaller. Compared to this amplitude, the next amplitude must be smaller. Compared to that amplitude, the next amplitude must be much more smaller. So this is what we call a damping situation. So in a damping situation, what really happens is the energy from the vibrating body due to damping, energy is removed from the vibrating system and dissipates this energy into other forms, internal energy, thermal energy, and does not return back to the vibrating system. Then dampers reduces what? The amplitude of vibration. Hence, what is happening to these oscillations? They are dying away quickly. Then other part I'll tell a bit later. For the moment, I explained how the graph would look like. But in here, there's a specialty. Even though the system is under damping, you can see that the time did not change. Why? If it is a simple pendulum, if the length of the pendulum is not changing, we can't change 2 pi square root L log G value. So as we can't change 2 pi square root L log G value, we can't change the time period. Isn't it? So M over K was the same thing. Then it means what? Even under damping, the vibration or the time period or the frequency, they would not change. Only thing is timely amplitude and the energy of the vibrating body would reduce. That is the idea about that. Okay. Then now that we will keep it in mind, separate. That story is different. Now a different story. What is the different story now? It is actually we are talking about a vibrating system. A vibrating system, that is, we are having a, let's say, like what you saw in that video, we are having a vibrator, let's say connected to a spring mass system. So this one, we can change the frequency of this vibration. Sorry. So let's say I'm, forget about the damping graph first. Let's say I'm giving 10 Hertz. When I give 10 Hertz to this vibrating body, then the spring mass system will also vibrate. Then I can find its maximum amplitude. I can find the time period. From that, I can find the maximum kinetic energy. So when the frequency is 10 Hertz, I'm getting the maximum kinetic energy. Then I can change that frequency to 20 Hertz. So at that moment also I can find this amplitude, the time period. It won't change, however, because it's the same M over K. Right? So time period would not change, but the amplitude would be greater. So when the frequency is 20, the kinetic energy that it vibrates would be much greater. Then the frequency 30, let's say. Right. Now, likewise, I can change the frequencies. Now, I'll go back to previous example to give you a proper idea. In the spring mass system, we found the vibrating time period to be 0.814. So 1 divided by 0.814 is equal to 1.23 hertz. 1.23 hertz. That means the natural frequency of this spring mass system is 1.23 hertz for this given mass and this given spring. So I'll take the same thing here, 1.23 hertz. 1.23 hertz. So I will use not 10, 20, 30, I will use 0.1, 0.2, 0.3, 0.4, and for respectively I will find. Now I can increase that value. So ultimately the place where I get 1.23 hertz for that particular spring mass system, at that moment I will see that this is vibrating in its maximum energy and amplitude. So it would have the greatest energy, maximum energy, maximum kinetic energy, maximum potential energy. Then if I increase the frequency furthermore, let's suppose it's 1.4 hertz now, then amplitude reduces again. 1.5 hertz, much more reducing. Likewise, it is reducing. So when I conduct this experiment and when I draw the graph for different frequencies, I saw that the maximum energy happened at a particular frequency. That is the frequency, that is what frequency? The natural frequency of the spring mass system. This is without damping. Now I will put this spring mass system in a water beaker. You saw that in the video. Then what happens when I keep it in the water beaker, 0.1 also, it will vibrate, it will have an energy, but not as much as earlier. 0.2 also, it would vibrate. Likewise, then for the same frequencies, if I get the data, they would be giving me the energy smaller than without damping situation. And another special thing is happening. Under damping situation, the spring mass system would give me a maximum energy at a frequency which is smaller than the natural frequency of the spring mass system when it is with no damp. So the graph got a bit skewed to the left hand side than no. So this is not a normal distribution graph. This graph is skewed to the left, okay? Skewed to the left. So not symmetrical in either side. So that is the idea behind that. So further things we'll discuss later. Then for the moment, it's enough. Then after a short time, 15 minutes time, we will start the maths class. Okay.
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 Nice.